solutions to
I'd have to think about that. Yeah.
use of matrices, and that's ugly.
Anyway, to continue from last time here, since we've hit 12:30 here, sorry, we're looking at dynamic programming solutions for for one of the problems that you're already well familiar with. That is the 0-1 knapsack problem. And just to remind you really quickly here about what the 0-1 knapsack problem is. Oops, sorry. There we go. Let me go over here and let's look at an actual input here. So this is the input that we're actually going to use later on here. You've got this list of items, right? Each item has a weight, each item has a value. And then you have this overall capacity, right? You can carry at most 7 pounds. So if you take, say, for example, the first 2 elements here, you're already at your weight capacity, but your value is something like 15, right? The total value over here is 15. Whereas if you had taken, say, the first element and this element right here, you can do a little bit better. A value of 17, and again, you are hitting your weight capacity. Another value here would be, taking the third element and the fifth element here. That hits your weight capacity the same way, but you have a value of 15 total. Let me make absolutely sure that this is going on. Yep, that's good. All right. Because it wasn't working the other day for this class or for some other class, I forget. No, for 155H, it wasn't working. Anyway, I just wanted to make sure that the recordings were correct. So, of course, if you had a much larger capacity, if you had a capacity that you could include everything, then of course there would be a trivial answer. If you have a weight capacity of, say, 0, what's the value of your optimal solution? Can you carry anything? No. Nope. So the value of the optimal solution is also 0. All right. What if now of course there are feasible solutions and then there are optimal solutions. What if, for example, you decided that your career in thievery was not the correct career at all, and you decided that you wanted to take nothing, right? In other words, the empty set, right? That you don't have to fill up your knapsack here, right? You could say, for example, take these 2, right? And that will hit a capacity of 6, leaving you 1 extra pound here, and that's going to be 15, value 15. But there's nothing to prevent you from going even lower, right? You could, of course, choose nothing. In which case, what is your value then? Your optimal value if you choose to take nothing? 0, right? So already we're well familiar with some of these quarter cases here. What we want to do now is develop a dynamic programming solution to this. And for that, last time we came up with this V sub ij, where that's, let me go ahead and copy this over here. That's the value of the optimal knapsack involving elements A1 through A sub I with a weight capacity of j. Okay? Let's go ahead and take that over here and think about this for a little bit. Okay? So again, I am considering only elements A1 through AI with an intermediate weight capacity sub j here. We identified last time the thing that we're actually interested in, but let's go ahead and review, what values of I and what values of j should we be considering. I is going to run from, say, 1 up to what? Actually, no, let's go ahead and rephrase that. Where should I start my I here? I'm going to consider these 5 elements, right? Consider initially where one of those corner cases where you take nothing. In other words, I will start at 0. Then you're going to consider, well, what if I took element 1? What if I took element 2? What if I took element 3, ... Where do I go up to? The last element is at element, well, in this case 5, and is going to be 5 in this case, and so I go up to n including n. Okay. This is going to be considering no elements. Let me go ahead and annotate this. Take no elements all the way up to your last consideration here. You take everything. Right? Now what about J for weights? I'm going to consider intermediate weight capacities. Well, what happens when I can't carry anything? Right? In other words, 0. You have no weight capacity at all. What's the trivial solution then? If you can't carry anything, what's the value of the optimal solution? Nothing. What if you could carry 1 pound? What if you could carry 2 pounds? ... What if you could carry everything up to this optimal, up to this given weight capacity right here? Right? So that's where I'm going to run up to. I'm going to run I from 0 up to n. I'm going to run j from 0 up to w to consider all these possible solutions up here. Now, let's think of some corner cases, some base cases. We've already identified a lot of them. What if I consider taking nothing? Then what's the value? 0. What if I consider a weight capacity of 0? You can't carry anything. What's the value there? Also 0. Right? Overall, what is my final optimal value? V sub n w, right? The last 2 elements in these sequences here. Because you've considered everything, and you've considered your maximum weight capacity given as part of the input of the problem. Yeah?
Did we say that weights are integers, or could they be?
Good observations. Generally, yes, we'll say that weights are integers. Because then the table, the tableau that we're eventually going to produce, you could have, an infinitely divisible table. Well, what happens when you can carry 2.5 pounds? Oh, okay. Well, what happens when you can carry 2.25 pounds? 2 1/8, 2 1/16, right? It doesn't have to be integer values as long as it's discrete values. And it's guaranteed to be discrete values because the input is discrete. The input is, here are all of the, here are 5 elements, right? Here are some weight capacities. It doesn't matter if it's 2.4, it doesn't matter if it's 3.8, it doesn't matter if it's 5.8, right? The number of combinations of those are going to be discrete, finite, and therefore you can associate associate all possible combinations with a discrete table, right? But for simplicity, we'll keep everything as integer values. At the end of the day, you can map everything to an integer value and then be done, right? And live under that assumption. Good observation, though. All right, so let me go ahead and annotate these as well. You can carry nothing, right? You can. This is the last the full capacity. Okay. Now let's get a hold on this thing right here. Let's think about V sub ij in terms of other solutions, right? So you are now considering including or excluding item A sub I. Right? Remember that we have a weight capacity of j. And now we're considering whether or not we should add item A sub I. Well, first of all, you ask yourself, is this even possible? Right? Can you carry item A sub I? Right? Here, oops, didn't mean to do that. Remember that we've got weight is going to be W sub I, and the value here is going to be V sub I. Okay? So 1 is taking A sub I even feasible. In other words, will it fit in our remaining weight capacity? So how do I know that it fits within my remaining weight capacity?
You take the remaining weight capacity and subtract weight.
All right, so my weight capacity right now is J, right? Because that's what I am keeping track of right now. And then I subtract, like you said, W sub I, right? And how do I know that that's feasible or not? All right, so if it's 0 or if it's positive, that means I've got some weight left over, right? This means it's feasible. What if it's negative? Right? For example, what if it weighs? I have a weight capacity of 5, but it weighs 7 pounds. Can you take that? Nope. So it's infeasible. If it's infeasible, do we even have a choice? If it's infeasible, no choice. You cannot take A sub I, right? Yeah, go ahead.
Does this take into account other solutions?
Well, not yet. We're just coming up with cases, and then we're going to look and find out what. Well, let's look at this one right now. You cannot take A sub I, right? Then what's your value? What's the optimal value of your of V sub ij here? I've chosen not to take A sub I, so that means I should consider elements A1, A2, dot, 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 A sub I minus 1, and here's A sub I, and I've chosen, or I can't take it, right? You don't take A sub I, right? That means that you have some other solution that involves A1 through A sub I minus 1. And because I didn't take it, my weight capacity is still, what was it? J. So what solution does that correspond to? Where you consider A1 through AI minus 1 and a weight capacity of J. Do we have something that expresses that? V sub I minus 1 J. Remember that our definition of V sub ij is that this is the value of the optimal solution involving some subset of elements A1 through AI minus 1 with weight capacity J. Right? So if I have no choice, then the optimal solution is already computed, and it's this value right here. Okay? Now what if I do have a choice? It is feasible. You can take this if you want to. Right? Then I have a choice. Don't take it or take it. If I don't take it, so let's go ahead and branch out here. Right? First one is take it. Take A sub I. And the second one is don't take A sub I. If I don't take A sub I, then we've already figured what that is, right? That's the same thing as down here, giving you this value right here. You don't take A sub I, and so therefore your optimal solution is going to be A1 through I minus 1, and you didn't take it, so your weight is unchanged. But now what about this? You do take A sub I. Right? It is feasible, and you've chosen to take it. Right? So take A sub I. My weight capacity goes down. My weight capacity was J before. What does it go to now? J minus whatever the weight of the ith element is. Right? This is my remaining capacity. Okay? And I've taken a sub I, a1, a2, dot, 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 a sub I minus 1, a sub I. And I've taken it and I've updated my weight capacity accordingly. So what is the value of the remainder of the solution? Again, v sub I minus 1. The optimal solution involving a1 through ai minus 1. But what's my weight capacity now? Whatever remains after taking the ith element. Okay? Now, how do I make a decision between this and, well, yeah, this? By the way, what else happens here? If you take a sub I, what do you get out of it? The value of the ith element. Right? So if you take it, you get the value of a sub I. Okay? So, how do you make your decision? Should I do this or should I do this? Should I take a sub I or should I leave a sub I?
If the value of
This one versus this one, you want to do what? You want to maximize your value, so you take the maximum, right? So all together here. So v sub ij, here's our recurrence that we just developed. It's going to be the maximum between v sub I minus 1 j and v sub I minus 1 j minus w sub I if the weight, if it's feasible. Otherwise, you're forced to make a decision that you can't take the ith element, and so because doing so would mean that you have a negative capacity, right? You've gone over your capacity. Right? So again, this corresponds to a choice. This corresponds to no choice. It's infeasible. Right. So all we have to do is take that and figure out how it relates to these other problems. That I sub j is dependent on this solution, but that's the same thing as this solution up here. Okay? So that means we're going to be drawing a table. This is the next part of dynamic programming. You are the fast method, you invert the solution or whatever the T stands for in the fast method. What was that T? Fast is going to be turn around the solution. All right? It's taking that top-down solution, that recursive solution, looking at the bottom and saying, oh, well, all you need to do is fill out this table. Okay? So let's go ahead and, first of all, identify the table. I'm going to run I and j. And we've already identified that I runs from 0, 1, 2, 3, dot, 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 up to n. Right? You're considering elements. And j is going to run from 0, 1, 2, 3, dot, 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 all the way up to big W. Okay? This is the one that we're interested in right here. This is the final solution where it's v sub n k. Now let's think about some of those base cases. Where I is 0, the value is 0. Where j is 0, the value is 0. So what does that correspond to with respect to this table? I is 0, you're not taking anything. The optimal value here will be all zeros on that row right there. Your weight capacity is 0. That means that you can't take anything. And so all of these would be zeros. Dot, 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 dot. Now let's think in general terms here. Let's think in terms of v sub I, j. This is the ith row, jth column. I want to get a hold of this thing right here. In fact, I think I could do a, oh, there, nice, cool. All right. V sub ij right there. What is it dependent on? It's dependent on I minus 1j, right? That appears in this one and this one. So where is that with respect to this table right here? It's right above it. I minus 1. So, there we go. V sub I minus 1j. All right, that's one right above it. Same column. Why same column? J is unchanged. So this is all the jth column right here. Okay? I can move these over a little bit. There we go. All right. So it's dependent on the one right above it versus, that was terrible. There we go. I can do better than that. There we go. That's still not that great. But anyway. All right. Versus this one right here. So what about I minus 1? That's one row up. But then what about this over here? Is it necessarily one column over? Jth column minus W sub I. W sub I is part of the input. It could be anything from 0 up to, well, infinity, but effectively W, right? So it's going to be somewhere over here. Come on. Okay, there we go. Yeah. So this is going to be V sub I minus 1, J minus W sub I. Right? So it's somewhere in the same row all the way over. Right? But it could be highly variable. It all depends on this W sub I right here. So one row up and but some number of columns over. Now, does that suggest how you fill this table out? If each answer is dependent on potentially the entire row right above it, what order should we fill this out in? Top to bottom, left to right. Right? So fill out this first row first, then the second row, then the third row, then the fourth row, dot, 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 until you get down to this last solution down here. Okay? So let's write out the pseudocode to do that. That should be pretty easy, right? For I running from 0 up to n, inclusive on both of those, by the way. For j running from 0 up to w, inclusive on those as well. What do I want to take care of as far as my base cases go? If I is 0 or if j is 0, then the value should be, oops, v sub ij should end up being 0. Okay? Otherwise, what? I end up doing this thing right here. Right? I end up doing, well, is it feasible or is it not feasible? If it's feasible, then yet I have two more choices right here. I take the maximum among these two. So let's go ahead and write that all out. Right? If it's feasible, else if, let's say that it's not feasible, first of all. So if j minus w sub I is less than 0, then I have no choice at all here. It's going to be v sub I minus 1 j. Right? Otherwise, it is feasible. Right? So I need to determine, well, what should I do? Should I do, should I take it or not take it? I would need to take the maximum. So else if, say, v sub I minus 1 j is greater than v sub I minus 1 j minus w sub I, then I don't take it. V sub I j is equal to v sub I minus 1 j. You could probably collapse these two conditions, by the way, into one block if you wanted to. I'm going to go ahead and make it so that there are 4 different blocks here. Else, oops, else v sub I j. Now, this one is larger. And by the way, I forgot here, v sub I. There we go. Again, what is this? I'll annotate it. This is the value of the AI item. Right? So if not taking it would be better than whatever solution you have if you did take it plus the value, realizing the fact that you did take it. If that's better, then leave it. Don't take it. So don't take a sub I. Otherwise, I will take it, and I'll end up getting its value. V sub I minus 1, j minus w sub I, plus v sub I. And that's it. All right? You end up filling this table out, top to bottom, left to right, and ensuring that this solution is available and this solution is available in order for you to make your comparisons. W sub I, V sub I, A sub I, those are all part of the input. Right? So it's not part of the table. Yeah?
So do we fill the entire table out, then start at the bottom right corner and work our way up?
Oh, good question. So how do we find out what our solution is? Right? Because even if we make a decision to take it at some point, ultimately later on, maybe the optimal value was not to take it, right? So we're making these intermediate decisions. How do we backtrack, like you said, to actually formulate the solution? Right? Before we do that, let's look at an example here. All right? Yeah, go ahead.
Yeah, I look at this a little bit last time.
Okay. This.
Okay, yeah, okay.
Here is an input for that input that we had before. Let me go ahead and pull that up so we can look at it over here. There it is over there. And here is the full table. Okay. Let's look at one particular input here, I guess. Let's look at this one right here. V sub 4, 5. V sub 4, comma 5. All right. How did we arrive at 12? All right. Well, first of all, we asked, can we take, right now we're considering whether or not to take element A sub 1 with a weight of 2 and a value of 7. So is it feasible? So 1, feasible? Question mark. That is, we take j minus w sub I, and is this greater than or equal to 0, or is it less than or less than 0? So let's plug these in. J in this case is 5. That means that I have a weight capacity of 5 minus w sub I. Well, what is w sub 4? 7. So can I take it? This is less than 0, so infeasible. So I have no choice here. I have to take v sub I, j, or sorry, v sub I minus 1, j. Well, where is that? Actually, no. Is it feasible? It should be feasible. J minus w sub 4.
I think you subtracted the
Oh,
value.
yeah, what am I doing? Yeah, thank you. Backtrack this, backtrack this, backtrack this. All right, minus what? What is the actual weight? 2. And that is greater than or equal to 0, so it is feasible. So I need to take the maximum among taking it, which is v sub I minus 1, j minus w sub I, plus the value sub I, which is equal to, so this will end up being v sub 3. Right? Again, it is I, j, 4, 5. So I minus 1 is going to give me 3. 5 minus w sub I. Well, we already computed that up here. So my new weight capacity is what? 3. Plus v sub 4, which is equal to Now, this one is just a table lookup. 3 and 3 gives me 5. The optimal value of considering everything up to and including element 3 with an intermediate weight capacity of 3 tells me that you can take some knapsack that is worth 5. So this is 5 plus, what's the value? 7. That's 12. That's what it ends up being. But for completeness, we have to take or don't take it, which would be v sub I minus 1 j, which is v sub 3. J is still 5 because you didn't take it. And that is also just a lookup. 10. So 10. Which one do I take? The one that's worth 12 or the one that's worth 10? 12. And that's where I end up getting this value right here. Okay? That's just one example. Of course, then you would go on and you would compute this one, and then you'd compute all these, and you'd finally get down to the fact that your optimal value here is going to be 19. Now, does anybody immediately see what values or what elements that corresponds to over here? It's not that obvious unless you start looking at some permutations, some combinations and stuff like that, and then you figure it out. Okay? So what we're going to do is we're going to develop an algorithm, at least the idea initially, of how do you, once you've got this table, how do you create the actual solution? Okay? Well, remember that this solution is dependent on the one immediately above it, and then something over here to the left somewhere. And I'm not even sure if that one's it. So look at the solution immediately above it. Right? It's different, right? What does that tell you about your decision-making process for choosing 19 here? You took it, right? In other words, what did you take? You were considering element 5 here. So if this is not equal, then this implies that you took a sub 5. Now, if you took a sub 5, what is your remaining weight capacity? I'm going to make this really small, put it up here. You took a sub 5 with a weight of 3. Your weight here was 7, so what is your new weight capacity? 4. Meaning that you go up one row and then 1, 2, 3, because this is your new weight capacity after having taken 5. Okay. Now I'm here, and I'll go back to red here. So I go up 1 and then over, over, over. That just corresponds to the weight right here. And I'll go ahead and circle these that I actually took it. Okay. Now, once again, look to the one above it. What can you tell me about the difference there? Did it change? Yes. So these two things are not equal. That implies that I took a sub 4. Okay. With a weight of 2, so I go over 1, 2, and now I'm right here. Okay. Look to the one above it. It's the same. So did I take a sub 3? Nope. These are equal. Equal. That implies that you did not take a sub 3. So I'll cross that off there. Now I'm up here. I look at A2 and A1. Are these the same? Nope. So that implies that I took A2. And I took it with at a cost, a weight of 2. So 1, 2. And at that point, what can you say about any of this when you hit these base cases over here? You are either out of weight to consider, or you are out of things to consider. So you stop. What was your overall solution here? A2, A4, and A5. Well, what's your value? 5, 7, and 7. That adds up to 19. And what was your total weight? 2, 2, and 3. 7. So you've hit your weight capacity. All you need is this table, and then you can backtrack and find the solution. Right? Eventually, you're going to hit one of these borders, and once you've hit this border or you've gone beyond it, actually, if you've gone beyond it, what does that mean? That you would have an infeasible solution and you screwed up somewhere, right? What happens if you went beyond this? Well, that could happen technically, I guess. It's just your index is out of bounds. Okay. All right. So yeah, go ahead.
What would happen then, I guess?
Well, it means that you have a bug if you went beyond the 0th column, because that would have said that's infeasible. You can't do that, so you are forced to choose something right above it. Right? Taking an example, well, you going from here to here. It probably wasn't infeasible. It just didn't buy you anything. Right? Yeah, something like that. Because you took A1, you cannot take A3, because then that would exceed your weight capacity. If you take A1 and A3, then your weight is 9, and that's greater than 7. Right? Yeah?
Should we assume then that there will be nothing that has equal both value and weight?
I don't that doesn't matter. That wouldn't impact anything. Right?
It might impact what exact things.
Oh, well, if it's feasible and you can take it or leave it and it gives you the same value, it doesn't matter. Right? It'll lead to an equivalent solution. There might be several solutions that are all the same weight, same value, maybe different weight capacities, maybe the same weight capacities. Right? For example, you could come up with uniform weights and uniform values. Then it doesn't matter what you take. Right? Just take some subset such that the values sum up to your weight capacity. So that shouldn't matter. Okay? So let's write this out as pseudocode. So we're given as input the tableau from V of 0, 1 knapsack. I don't, unlike like Floyd Varshall or Dijkstra's or anything, there's no name associated with this usually. So it's either the person that did it wasn't a big enough name that, oh, that's Joe's algorithm, or that's Joe's table, or something like that, or it just never caught on or something. Who knows? But our output will be the optimal knapsack S, which is some subset of all the elements, A1 through AN. Okay? Initially, we're going to start out with the empty set. It could be possible that that the only valid and feasible solution is the empty set, in which case your entire table is a bunch of zeros. Right? I will initialize my I here to be n, right? All I'm doing is I'm starting at the bottom of this table right here, and I'm working my way up and to the left. So I'll start at the bottom, start at the bottom. Remember, I'm just building this solution. We already did the pseudocode for filling out the table, right? This is the pseudocode for building the solution once you have the table. Then I will start my J at W. And again, this is start at the last column. And I will go into a while loop here. While I is greater than or equal to 0, and j is greater than or equal to 0, I will do the following. These are just bounds, right? Just make sure that I stay in bounds. Stay in bounds of the table. Once you're out of bounds of the table, you're done, right? You've fallen off the face of the earth, or you've fallen off the other edge somewhere, right? And then I'm going to have another while loop here, and we'll explain this in a second here. While I is greater than or equal to 1, and v sub I j is equal to v sub I minus 1 j, I'll do the following. What is this capturing here? What is this idea capturing? So v sub ij is equal to the one right above it, right? While that's true, keep moving up until you hit this this row right here. If you had a bunch of these, like say 10, 10, 10, right, and you happen to be at this one, you need to go up until the next one is not equal. That loop stops you at the point that you found an element that you need to take. Right? So I'm going to take a sub I. Actually, I'll travel up here, I up, minus, minus. And then I will add the ith element. There we go. What do I need to do now with j and I? Well, what about I? That should be easy. So here's a sub 4. You take it. To set yourself up for the next loop, what should you do? Are you considering a sub 4 anymore? You already took it. So move up 1. Right? And consider a sub 3. What about my j? What did I do over here in this example? If I took this element, a sub 5, then I went up 1, but then I went over how many? As many as the weight of the thing that you took, which in this case is w sub I. So j minus w sub I. Okay? And that's it. You output s at the end. Now here's the trick. Let's do an analysis of this. Right. Forget about building the solution. Let's focus on filling out this table. Right? How big is this table, first of all? So, analysis. The size of the table is what? N by what?
W.
Times W, right? Now, you are forgetting the 0 and the 0, so it'd be technically n plus 1, w plus 1 by w plus 1. Forget about that, right? Plus 1, minus 1, we're looking for a big O analysis here, right? So, thus, filling out the table is order nw, right? Okay, so can you treat w as a constant? If so, it looks, and here I'll emphasize that, looks to be linear. It's going to be order n, right? Except it's not. Can you treat w as a constant? Just because it's not n? No. It could be that w is order 2 to the n. Right?
Oh, because W can be whatever the heck.
W could be huge, right? Now, it can't be that big, right? It can't be infinite, because if the input size is n, you only have n bits to work with, right? Generally, the input size is bounded by some value. Suppose n, right? Because you're given n things, you're given n weights, you're given n values, you are given w, which can be bound by the number of bits, right? So what is the maximum value you can represent if you have n bits? If I gave you 5 bits, so let's say 2 bits, what's the maximum value that you can represent? 1, 1. What is that? 3, okay. If I gave you 4 bits, 1, 1, 1, 1, what's the maximum value that you can represent? What is 1, 1, 1, 1, 1? 7, all right. If I gave you 10 bits, what's the maximum value that you can represent? Nobody off the top of your head? 1023?
Yeah, that.
Well, you got to get used to powers of 2 because you're all computer scientists and computer engineers, right? 10, that's going to be 1,000, right? The nearest power of 2 greater than 1,000, which is 1,024, and then subtract 1. Why? Because you start at 0. Right? So if you have n bits, what's the maximum value you can represent? 2 to the n minus 1. Why minus 1? Because, of course, you start at 0. Right? So this is this algorithm is what we call pseudo linear. Right? The analysis is hiding the true complexity if you ignore W. So you can't ignore W. It could be exponential with respect to the number of elements in there. Right? If I've got 5 elements, W could be 1,000, million, trillion, whatever. Right? It could be it doesn't have to be it has to be bounded. It can't be infinite, but it could be bounded by some constant with respect to 2 to the n. Right? So you can't ignore W. Right? The 0-1 knapsack problem, 0-1 knapsack problem is NP. Does this work? Nope. Is Math SF. Every year I have to pull out Math SF for this. NP complete. No polynomial time algorithm is known for it, or even thought to exist. For those who think that P is not equal to NP. Those who think that P is equal to NP are in the extreme minority or crackpots. Right? So what is P and what is NP? That's what we're going to get into next after dynamic programming. For now, just think of NP as these really, really difficult problems. Nobody knows any efficient polynomial time solutions for them. Here's one of them, the dynamic 0-1 knapsack problem. What was your original solution, by the way? Our original solution on homework 1 or 2 or whatever it was. It was combinatorial. You generated all possible subsets, which was 2 to the n. That's an exponential time algorithm. Yes, you did some pruning. Yes, you did some heuristics to cut out infeasible solutions. But at worst case scenario, it was still going to be exponential. The only algorithms that we know of for NP complete problems are going to be exponential time algorithms. This is no different. Just because it looks to be linear, that would be us ignoring the fact that we have this other parameter over here that could be exponential in n. Meaning that this this table that you're filling out could be huge. It could be short, but it could be exponentially sized width. Right? And filling that out is not going to be done in polynomial time. Right? We can come up with an example that you say even 100 elements. So that's relatively small. But let's say that the weight capacity, total weight capacity is 2 to the 100. Are you going to be filling out a 2 to the 100 table in your lifetimes? No. Nope. Are you even going to be able to, is there even a computer on Earth or all the computers on Earth that can store all that all at once? Take the combined computation storage for the entire history of mankind, assuming that we've had computers for 3,000 years even, and it can't be done. Right? You can't store all that stuff. You can store numbers that big, right? 2 to the 100, that's just one number, but it's a compact representation. It only has 100 bits, right? But its value, its magnitude, is actually 2 to the 100. And if that ends up being the width of your table, it's way too big. Yeah?
So how does the CS grader?
I don't give you anything that big.
Oh, okay.
I mean, the same on homework 1 when you did it with a brute force exponential time algorithm. It still ran, right? All right, we'll look at another dynamic programming problem next time.